Okay. So here was the situation yesterday. We started this problem. We didn't get to finish it. A boat leaves a marina. Okay, so in my picture here, I've just labeled a point. I've called that the marina. It says that first the boat is going to travel 6 miles in a direction north 20 degrees east. Now, when we're talking about bearings yesterday, the first direction's really your starting point, and then the second is which direction you're rotating from towards. Okay, so really we're saying we're going 20 degrees east of the north position. Okay, so starting in the north, what I did. So anytime you draw a point too, you're going to notice you're going to get these are all oblique triangle problems, these bearings ones. Okay, so here's the marina. What you can do is you can draw a dashed vertical line through that point, and then from the north position, the boat's going to head in a direction 20 degrees to the east. Okay, so I have this first little given angle is 20 degrees, and then the boat travels 6 miles in that direction. Okay, where now the boat's going to turn right and continue 5 miles in a direction south 50 degrees east. Okay, so again, at this turning point, I've drawn another dashed line through it. And this time your starting or your reference direction is south, and we're going to rotate 50 degrees towards the east direction. Also, it might be helpful you might want to draw this down for yourself to, and this is no pun intended, get your bearings. Apparently I don't have my bearings. To the right is east, to the left is west, straight downward is south. Okay, so when I say south 50 degrees towards the east, we're rotating this way, and I can draw my little 50-degree angle right here. Okay. Now, and then we know this side was 6 miles. That was your first, how far you traveled in the first direction, and then you traveled 5 miles in the second. Okay. And then once we get to this point, we need to know how far we have to travel to get to the marina. And then this little angle theta I've drawn down here, that's the angle that's going to give me my directions or bearings for that heading. Okay. Now I've drawn this picture up here for everybody. Notice that all 3 of my points, this will be very helpful. Make sure you draw these dashed vertical lines going through all those points in your triangle. That'll certainly help you find all the other angles. Ben?
For beta, wouldn't beta be the angle from the line continued from the course it was going rather than the north-south line? Do you see what I'm saying?
Well, beta is really going to be a collection of two angles.
Excuse me, beta, I said.
The alpha or the gamma?
Beta. Not beta.
Oh, theta.
Yeah,
this one?
Heading, he's still pointing that direction. He hasn't made any turns. Do you see what I'm saying?
Yeah, I mean, once you stop here, I mean, he's going to have to turn. We're not going to really focus on left, right, up, down. Doesn't really matter. I just need to know the heading I'm going in.
Oh,
so we're at this position. I need a reference, which we're going to use south. And the answer is going to be we're going to start from the south and rotate theta degrees towards the west. So the answer to this question is going to be south theta degrees west when we're done. We just have to find that theta. Okay, but let me get to that first. I got to build up to what theta is. Okay, so first, once you've drawn all these all these vertical dashed lines through all of your points, that was your first heading 20 degrees. And then I think I drew this down yesterday. If you take a line segment and you draw 2 vertical dashed lines, this is called I forget what it's called in geometry. It's like the opposite angle identity or something like that. I don't really remember the name. But if this angle's alpha, then the opposite angle also has to be alpha. And if this angle up here is beta, then this angle down here has to also be beta. So in my picture, if this is 20 degrees, I have this line segment right here, and I have this dashed line. This little opposite angle has to be 20. Okay? And then now, the second direction, starting from the south, we went 50 degrees to the east. This little angle is going to be 50 degrees. That was from the heading. And then this opposite angle also has to be 50 degrees. Okay? Now, we're going to call this the angle in the bottom right corner, let's call that gamma. And then the actual angle that gives us the heading to get back to the marina, we'll call that theta. And the trick for finding theta is, once you find gamma, all three of these angles have to add up to 180 degrees. So theta is going to be 180 minus gamma minus 50. Okay, so make sure you draw all these vertical dashed lines. Use your opposite angle identity, whatever you want to call it. Okay, and then that'll give you at least one angle inside the triangle, and it'll help you find the angle that gives you the heading. Okay, so what I've done now is, since this little angle is 20 and that angle is 50, I pulled the oblique triangle out, so that total angle would be 70. That's our 6 miles for our first direction. That's the 5 miles for the second. Once I find the distance, that'll solve for part A. And then once I find this gamma, I can find theta by doing 180 minus the gamma and the 50. And then yesterday what we did to first find the distance we must travel, I used law of cosines at this point. Really it's d squared equals the sum of the squares of the other two sides minus twice the product of the length of the other two sides times cosine the angle between. And to solve for that distance, I took square root on both sides. And I think, did we get 6.36?
Yeah.
Okay. So we got the distance. Okay. And then now I can find gamma. Anybody have an idea of how to find this angle?
Law of sines.
I can use law of sines because is gamma really going to be the largest angle? Technically the 70 degrees would be the longest angle because this is the longest side. So in general you're always safe. If you use if you don't use law of sines to find the largest angle, you're good. Okay. All right. Yeah.
What happens if you do use it to find the largest angle?
So if the largest angle ends up being obtuse and you use law of sines, you get an angle between like 0 and 90 degrees. So you'd have to do 180 minus the angle you found. In general, though, I just try to avoid using law of sines to find the largest angle.
Okay.
And then you'll be safe. Okay. I like being safe, as opposed to, taking a gamble or a risk and having to adjust things. That's typically where I tend to see more mistakes as well. Okay. All right, and then to find this gamma, we can use law of sines here. So now we know sine gamma over the length of its opposite side 6 is going to be sine of that 70 degree angle over its opposite side, which we approximated to 6.36 miles. Okay. Is it okay if I get rid of my north, west, east, south little thing here? My compass bearings. Okay, and then I can multiply both sides by 6, and then to get gamma, take the arc sine or sine inverse. So gamma is going to be sine inverse of 6 sine 70 degrees over 6.36.
I got 62.44. Yeah.
Okay. And that's the other thing too, is make sure you're writing the degree symbol. I saw a lot of people miss that on the homework. I didn't take any points off, I just wrote it in. Okay. And then the other thing is, I'll make sure I tell you how to round on the test. Okay, again, I threw the quiz together, I didn't have time to fix it, so.
And then we do 180 minus the 62 minus the 70.
Yep. And then now once you know gamma, like Kirsten
50,
said.
50, not 70, sorry.
Yep. So once I know gamma, to find the angle that gives the bearing, I can do theta is going to be 180 degrees minus those two. So theta is 180 degrees minus 50 degrees minus 62.44.
I got 67.56.
And you get 67.56. So once the boat has stopped and needs to get back to the marina, boat must travel south 67.56 degrees west. So again, the first direction south is your starting point, and we're rotating 67.56 degrees towards the west. Okay. So again, I think the hard part here is using your bearings to find the angles inside of the oblique triangle. Yeah, that's coming from this part right here. So once I knew my original bearing, that opposite angle right inside up here would be 20 as well. And then the second bearing, beta, is going to give me this little angle right here. And then the next goal would be to find the angle inside the triangle. And then the one that gives you the bearing is 180 minus those two. Okay. So a couple more things. So that's essentially the only applications I'm really going to throw at you are similar to the examples we did yesterday where you have to find the height of various objects. You can use right triangle trig, I think, exclusively there if you want. And then your compass bearing questions or your bearing questions are almost always going to end up in solving an oblique triangle. And it always ends up essentially being side angle side. Okay? And if I remember correctly, a side angle side triangle, that's always using law of cosines first to find the length of the third side. And then as long as the angle you're looking for isn't obtuse or the largest angle, using law of sines works just fine. Okay. And then, ooh, wow. So 10 minutes left. I might have to finish one of these parts on Monday. Start vectors, and then I might have to steal a couple minutes on Wednesday to finish off the vectors, but most of the class period will be review, and then Thursday will also be review. Okay, so last part, what we're going to do is, in a previous section, in chapter 4, we simplified compositions of, trig functions with inverse trig functions. Okay, but we actually found specific values. So what we're going to do now is we're going to simplify functions that are compositions of trig functions and inverse trig functions and other types of functions. So let me show you what I mean. So simplify tangent arc cosine 3x and find the domain. This wasn't on the handout, but we're going to find the domain. Now, let me explain what it means by simplify. So this is a function of x that's technically a composition of tangent with arc cosine and the function 3x. This is a triple composition. Okay. And what I'm going to do is I'm going to use right triangle trigonometry. I'll be able to write this as a like a rational function or a function involving radicals that does not involve any trig functions at all. Okay. So let me show you the procedure here. Okay, so you're always going to take this inside function. We'll talk about the domain in a second. So what does arc cosine of an input do? It always outputs an angle. Okay, so I'm going to think of that whole arc cosine of 3x as some angle theta. And we're going to make a substitution. So let's let theta equal the arc cosine. I always forget that second c. Arc cos of 3x. Okay. And then from here, we're going to convert this back into terms of just cosine. Okay, well, if theta's arc cosine of 3x, what happens if I try to rewrite this in terms of cosine? So the output's going to become the input, and the input becomes the output. So I'm using that idea of converting an inverse function to terms of the original. Okay. And now we're going to use an idea we used in section 5.1. If I know that cosine of an angle in a right triangle equals some value, I should be able to draw a triangle. A right triangle with this angle theta in it. Okay, we did this before, right? Like if you knew cosine theta was 1/2, then we could label the sides in the right triangle. And then what was the trick, right? Cosine's really adjacent over hypotenuse. How can I really think of 3x as a fraction?
3x over
3x over 1.
Yeah, the easy way to turn it into a fraction is to divide by positive 1. And since cosine theta is adjacent over hypotenuse, I can call the bottom side 3x, and I can label the hypotenuse with positive 1. Okay, so I start out, if I want to simplify this, just call the inside function some angle theta. So make a substitution. Convert back to terms of the original function. If you need to make the right-hand side look like a fraction, if it's not already, you can just divide by 1. And then since cosine of an angle is adjacent over hypotenuse, I can call the adjacent side 3x and label the hypotenuse 1. Okay. And then really what I'm doing now is I'm just using this triangle, and we're going to see what tangent theta is. Okay. So what we have so far is tangent arc cosine 3x. I can write this as tangent of theta. And now using this triangle, if I want tangent of this angle, I need the opposite side divided by the adjacent side.
My only quick question
Yeah.
is, how do we know it's going to be a right triangle? Do we just make a right triangle?
SOHCAHTOA, right?
Well, yeah.
The definition of cosine of an angle is opposite over adjacent. So I can just pretend that this is an angle in a right triangle. Okay.
Just making sure.
Yep. So I'm using the SOHCAHTOA definition of cosine. Okay. All right. And then what I have to do is I have to find the length of this opposite side. Is it probably better? Let's actually call it op, since it is opposite the angle theta. Okay. So how am I going to do this? How do I find the length of that opposite side?
You have your hypotenuse squared minus your other side squared.
Okay, so you're really using, Kirsten, were you going to say it?
Pythagorean theorem.
Yeah, the Pythagorean theorem, right? The P thing, right?
Pythagorean.
Okay, so Ben, you're right, but I'm just gonna write down the property first. Op squared plus 3x squared should equal positive 1 squared, the hypotenuse squared. So that's Pythagorean theorem. And then op, when you're done, I'm skipping some steps here. So first of all, 3x squared is really
9x squared.
9x squared. So I subtract that to the right and take a square root. The opposite side will be the square root of 1 minus 9x squared. And hold on, I don't like how I wrote. There we go. Okay, so the original function, we made a substitution called the inside part theta. And now using that right triangle, tangent of theta would be the opposite side over the adjacent side.
Do you not need the square root on top?
Oh, yeah. I forgot the square root. And I forgot to write it over here too, didn't I? Thank you. So generally, if you have a composition of trig functions, inverse trig functions, and they're functions of x, you should be able to use this approach to rewrite that as a rational function, or, you know, in this case, it's kind of like a rational function, except for the numerator has a radical up there. Okay. And then, since I have 4 minutes left, I think I have time to find the domain, and we'll do the other part when we come back on Monday. So let me review one more time, just real quick. Okay, so I want to simplify this composition, tangent of arc cosine of 3x. Since what do we really plug into trig functions? We really plug angles into them. So you can let this whole inside part be some angle theta. Convert back to terms of the original function cosine. And then since cosine of an angle, we can treat that angle as being in a right triangle, and cosine is adjacent over hypotenuse. If it's not already a fraction, just divide it by 1. Okay, so that allows me to label adjacent side and hypotenuse. You can use Pythagorean theorem to get the opposite side. And then finally, tangent of that angle theta will be opposite over adjacent. Okay. So that's how you can convert this trig function into a function from like pre-cal 1. Yeah?
So does tangent go away or something? That's the answer for theta.
No, this is tangent of arc sine of 3x. But since I made the substitution, I said theta is arc cos of 3x. this is the same as tangent theta. And then I found all the sides in the right triangle. Tangent of an angle is op over adjacent, op over adjacent. So yeah, the trig functions are gone. Okay, so usually if you take a trig function and compose it with an inverse trig function, when you simplify, the result isn't going to have any trig functions at all.
Can we do like tangent theta equals that as our answer?
Yeah, I mean this, I would prefer to see you write the original function equals this right here.
Okay.
So that is the answer. And the only thing left is finding the domain. It's the same process every time. Inside function's the angle. Make the substitution. Convert to the original trig function. Draw a right triangle. Find all the sides. And then, since I made the substitution, the inside part's theta, tangent of theta in that right triangle you created is op over adjacent. Okay, and then now, I gotta find domain. So here's my start. So here's the original function, tangent arc cosine 3x. Okay. And by the way, this is really useful in calculus, so that's why I'm making sure I cover it. It's not like I'm just doing this for the sake of it. If I'm teaching this as a pre-calculus class, as a precursor, I have to at least teach all the things you're going to use there. Okay, so what I'm going to do is I'm going to look at this inside part, and I'm going to try and find the domain of this first. Okay, so if I'm just considering arc cosine of 3x, and I want to find the domain, does anyone remember what the domain of arc cosine is? It's going to be the range, yeah, what was that? Yeah, perfect, right? Because the domain of arc cosine is the range of cosine, which is between -1 and 1. So the input 3x has to be between -1 and 1. And if I want to know what the acceptable values of x are, I'll divide by 3 on both sides. Okay. So for starters, for sure, x has to be between -1/3 and 1/3. Okay, but that's not going to quite give me the domain. I know a lot of you are anxious to get out of here and it's Friday, but please bear with me for a second. Okay. All right. That would also make sense, because if you look at the function it's simplified to, unless x is between -1/3 and 1/3, you'd get a negative number underneath the square root, which is no good. Okay. But there's one little thing that doesn't quite work, because one of these values between -1/3 and 1/3, if I plug it into this arc cosine, I might get like pi over 2 or something, which is not in the domain of tangent. Okay, so now what I have to say is, okay, so what's the range of this function now? So the range of arc cos of 3x. Does anyone remember what kind of angles arc cosine spits out? They're always between, so the range of arc cosine. Well, remember for building arc cosine, you had to restrict the domain of cosine to 0 to pi.
Yeah.
So the range of arc cosine is the interval 0 to pi. Because that's the domain of the restricted cosine. Now the problem is one of these x values is going to spit out pi over 2. But tangent's not defined at pi over 2. Anybody have a guess at what x value I'm going to actually have to end up omitting?
0.
Yeah, I think it's going to end up being 0, because arc cosine of 0, what's an angle that has a cosine value of 0? It's pi over 2. But, so what I'm going to say is the range of arc cosine is 0 to pi, but pi over 2 is not in the domain of tangent. Okay. And since arc cosine of 3 times 0 equals pi over 2, 0 is not in the domain of the, and this is the last thing I have to say. I'm going to do this because I'm short on time. I'm going to call that f of x. So 0 is not in the domain of our original function. So basically this is my domain, I just have to throw out 0. So the domain D is minus 1/3 to 0 union 0 to 1/3. And I apologize, it's a little bit rushed. I would have liked to do it slower. That's why I did record it as well. Okay. So I'll see everybody on Monday. Have a great weekend. I'll again be generous when I grade the part B of the quiz.